Hello, my rubber hearts. Did you ever notice how some rubber products are super stretchy while others feel tough and rigid? The secret lies in the structure of the polymers, whether they are amorphous, crystalline, or somewhere in between. But why does this matter? Because it determines how rubber behaves from flexibility to strength and even heat resistance. Stick around to see how these structures shape everything from tires to seals and why understanding this is a game changer for rubber technologists. We will also take a look at some common polymers used in rubber compounding and discuss why knowing whether a polymer is amorphous, crystalline, or semi-crystalline matters when creating high-performance rubber products. So let's jump in. Let's start by breaking down the basic definitions. An amorphous polymer is one where the polymer chains are arranged in a random, disordered fashion, almost like a bowl of tangled spaghetti. There is no long-range order to how the chains are packed. Because of this disorganized structure, amorphous polymers tend to be softer and more flexible, often transparent, since light can pass through without being scattered, and they have no clear melting point, but instead soften gradually as they are heated. One common example of an amorphous polymer is natural rubber, or NR, which in its raw state has a randomly arranged molecular structure that gives it its flexibility and elasticity. On the other hand, crystalline polymers have polymer chains that are arranged in a highly ordered, highly packed structure, much like how atoms are arranged in a crystal. This level of organization makes crystalline polymers stronger and more rigid, typically opaque because the regular structure scatters light, and they have a well-defined melting point, as more energy is needed to break the orderly structure apart. A good example of a crystalline polymer is high-density polyethylene, which has a highly ordered molecular structure that gives it its strength and durability. This being said, most polymers in practical use are not entirely amorphous or crystalline. They are semi-crystalline, meaning they have both amorphous regions and crystalline regions. The degree of crystallinity varies depending on the polymer and how it's processed. In semi-crystalline polymers, the crystalline regions provide strength and toughness, while the amorphous regions contribute flexibility and impact resistance. For example, polypropylene and nylon are semi-crystalline polymers with both ordered and disordered areas in their structure. This gives them a good balance between rigidity and flexibility. By now, you might be wondering, how do these structures occur? The structure of a polymer, whether it's amorphous, crystalline, or semi-crystalline, depends on several factors. Polymer structure and regularity, because polymers with a regular symmetrical structure are more likely to form crystalline regions. For example, polymers like polypropylene have repeating units that allow the chains to pack together neatly. On the other hand, polymers with irregular or bulky side groups, like natural rubber, are less likely to form crystalline regions because the irregular structure prevents the chains from aligning. Cooling rate matters because when a polymer is melted and then cooled, the speed at which it cools affects whether it becomes more crystalline or stays amorphous. Slow cooling gives the chains time to align and form crystalline regions, while fast cooling traps the polymer chains in a random amorphous state. Processing techniques impact crystallinity because mechanical stretching or drawing of a polymer can cause the chains to align, increasing crystallinity. This is often done during the production of fibers or films. Now that we have covered the basics, let's talk about some common polymers used in rubber compounding and their crystallinity. Natural rubber is amorphous at room temperature but can develop crystalline regions when stretched or cooled slowly. Its amorphous structure gives it excellent elasticity and flexibility, making it ideal for tires, hoses, and seals. However, Its tendency to crystallize under strain can improve its strength and toughness when needed. Styrene butadiene rubber is amorphous and it is mainly used in applications like tires, where flexibility and good wear resistance are important. Its amorphous nature means it performs well in environments requiring elastic properties without becoming brittle. Butyl rubber is amorphous and is highly impermeable to gases, making it great for inner tubes and air retention applications. Its low crystallinity ensures that it remains soft and flexible even at low temperatures. Ethylene propylene diene monomer is semi-crystalline and is used for weather stripping, seals, and automotive parts. Its crystalline regions provide the strength needed for outdoor applications, while its amorphous region keeps it flexible and resistant to heat and weathering. Polypropylene is semi-crystalline and often used in products requiring rigidity and chemical resistance. Polypropylene's crystallinity gives it toughness, while the amorphous regions ensure it's not too brittle. So, why does it matter if a polymer is amorphous, crystalline, or semi-crystalline when formulating a rubber compound? The degree of crystallinity directly affects a polymer's mechanical properties. A more crystalline polymer is stronger and more resistant to deformation, while a more amorphous polymer is softer and more flexible. This is why natural rubber, which is amorphous, is so elastic, while semi-crystalline polymers like polyethylene are more rigid and strong. A compounding technologist needs to consider whether the final product requires flexibility, rigidity, or a balance of both. For example, tires need some crystallinity for strength, but not too much crystallinity because that could make them brittle and less capable of withstanding impacts, while seals and gaskets require flexibility, so amorphous polymers are often used. Crystallinity also affects how a polymer behaves when exposed to heat. Crystalline polymers have a clear melting point, while amorphous polymers soften gradually. This is important when designing rubber compounds for high temperature environments. For example, EPDM, with its semi crystalline nature, is often chosen for heat resistant applications because its crystalline region maintains structural integrity at higher temperatures. The processability of a polymer, or how easy it is to mold, extrude, or form, can also depend on its crystallinity. Amorphous polymers are generally easier to process because they soften more gradually and have a lower viscosity when melted. Crystalline polymers, on the other hand, need higher temperature to process and can be more challenging to mold because of their rigidity. A compounder must strike a balance between easy processing and high performance. For example, SBR, being amorphous, is easier to process and shape, making it ideal for tires and footwear manufacturing, while butyl rubber, with its semi-crystalline structure, is often used in products requiring rigidity and chemical resistance. Butyl rubber's crystallinity gives it toughness, while the amorphous regions ensure it's not too brittle. When working with rubber formulations, it is important for a rubber technologist to understand how the degree of crystallinity in a polymer affects also the final properties of the product. Here are some key points to consider. Balancing flexibility and strength, because a material with more crystalline regions will be stronger but less flexible. For products like tires, you need the right balance. Too much crystallinity and the tire becomes brittle. Too little and it won't be strong enough. Heat resistance, especially in applications exposed to high temperatures such as automotive parts or seals. A polymer with semi-crystalline properties like EPDM can maintain its performance better than a fully amorphous polymer. Processing adjustments, because understanding whether a polymer is crystalline or amorphous helps you decide the processing temperature, mixing times, and the types of filler or additives that can be used to optimize the final product. So, amorphous, crystalline, and semi-crystalline polymers Each have unique properties that affect how they behave in rubber formulations. Understanding these differences is crucial for rubber technologists when deciding how to compound rubber for specific applications. By balancing the right amount of flexibility, strength, and heat resistance, you can create rubber products that perform optimally in their intended environment. And that's it for today, my rubber hearts. If you found this episode helpful, don't forget to like and subscribe to the channel for more insights into the science of rubber. Let me know in the comment if there are any topics you would like to learn more about next. Until next time, stay elastic and stay curious.